Hello everyone. In this video I would like to show you how to model reactions using OpenHydroQual. So what I'm going to do is that I'll just come up with this very simple system which consists of just a single batch reactor, and then I'll try to make models of different types of reactions. I'll start simple. So here are the reactions that I'll model. So first what I will do is that I'll just model a simple first order decay. Okay, so basically the rate of reaction, I'm just gonna basically introduce this hypothetical reactant or chemical called A, and then I'll apply a first order reaction to it. So as you can see, this is the rate of reaction, and then the ordinary differential equation will look like this equation right here. Then I'll introduce a new hypothetical chemical called B, and then I'll apply a second order decay to it. So here this is going to be the um, reaction rate expression, and the ordinary differential equation that OpenHydroQual will solve is going to be this second equation right here. Then what I will do is that I'll change our first order reaction to a Michaelis-Menten or monode kinetics. So I'll introduce a new parameter called K sub S, which is going to be our half saturation constant, and then I'll just change the reaction that we created in the first item to a Michaelis-Menten. And as a fourth step, what I will do is that I'll keep this Michaelis-Menten kinetics, but I will make the reaction rate temperature dependent. And we'll use this simplified Arrhenius equation to do that. I'm going to use a theta of 1.05 and a reference temperature of 20 degrees Celsius as is typically done. Okay, so I'm going to keep this page in the background, and I'm going to go back and forth to this page to at different stages of my work. So I'm going to open HydroQual. First thing I'll do is that I'll add this reactor component. By the way, it doesn't have to be a reactor component. You can apply these reactions to any block component in OpenHydroQual. So you may have soil, you may have a pond, a reservoir, anything, and the reactions will work the same way. If you have transport, flow and transport, of course the flow and transport will also be modeled. But in this example, I want to keep it simple, so I'll stick to a batch reactor. So the first thing what I will do is that I need to add a reactor plugin. So I'll go to preferences, I'll click on add plugin, and basically I'll just scroll down to get this mass transfer. So mass transfer plugin will contain a batch reactor, or actually a reactor. It doesn't have to be batch. We can have inflow and outflow, but I'm not gonna include an inflow and outflow in this case. So I'll just pick the mass transfer plugin. So what it will do is that it will add a bunch of components for me, but the one that I'm gonna use is going to be this one, which is a reactor. So I'm gonna click on it, and I have my reactor. It's called reactor 1. If you want to change the name, feel free to do that, but I'm gonna keep it as reactor 1. Now the only thing that we need to provide as a property of reactor 1 is the initial storage, which is going to be the volume of the reactor. Um, so basically, and it's going to stay the same during the simulation because I don't have any inflows and outflows. So what I'm going to do, I'm just going to say the initial storage is going to be 1 cubic meter. So essentially what we have is that we have a reactor with a volume of 1 cubic meters. And now, so I can actually run the model. What I'm going to do is that I'll just save it. So let me save it as, I'm going to save it in my Dropbox. I have this folder where I save all the examples of OpenHydroQual. So I'm going to save it as reaction example. Okay, so now what I want to do is that I want to introduce the constituents. So basically the first constituent I'm going to introduce is going to be a constituent called A, and then I'll apply the first order reaction to it. So how to do that? Basically here is a chemical constituent. So if I click on this icon, I'm going to get a chemical constituent. So I'm going to click on this, and then under my constituents I have this constituent 1. I'm going to change the name to A. So basically we can also provide a diffusion coefficient for this constituent A, but since I don't have any transport, I'm going to leave the diffusion coefficient as 0. So that's it. So we have a constituent A. What I can do at this time is that I can introduce some constituent A to my reactor. So basically that's going to be my initial condition. So if I now click on the reactor and go to the properties, I'm going to see this item called A colon concentration added to the properties. And I'm going to go ahead and say the initial concentration, let's say, is 2 grams per cubic meters. So we have 2 grams per cubic meters of A. Actually, what I'm going to do is that I'll just run the model to see what will happen. We still don't have a reaction. So basically A is treated as a conservative tracer introduced to our reactor, and we shouldn't see anything interesting, but I'm just going to run it to make sure things work. So basically in order to run, by the way, you go to this you just expand the toolbar, and we pick this gentleman who's running. That's the bottom that will run the model. Now let's look at some of the results. So basically what I'm going to do, I can right click on the reactor and go to basically pick this results menu, and then I have a bunch of outputs. I can look at the storage. So the storage, as you remember, we set it to be equal to 1 cubic meters. So it's 1, and it stays 1 during the course of simulation, which is a little longer than 1 day. Technically it has to be 1 day, but it goes a little further. Then I can also look at, for example, I don't know, the mass of A, the concentration of A. So I'm gonna look at the concentration of A. So basically it's 2 grams per cubic meters, and it stays 2 throughout the simulation. That's because we don't have any reactions going on. Okay. Now, so next step, what I'm going to do is that I will introduce my reaction. So in order to do that, first thing what I want to do is that I want to add a reaction parameter, which is going to be our decay rate constant K sub A. So in order to do that, basically there's this icon. I'm sorry, actually this icon is called reaction parameter. So basically it's a reaction, there's some chemical stuff going on, and then we have this icon that represents parameters. So I'm going to click on that one, and then what it will do is that it will add a reaction parameter for me. So if I go to the object browser, under reaction parameters, I'm going to have this item called reaction parameter _1. I'm going to change that. I decided to call this K sub A. So I'm going to change the name to K sub A. And at this time, all I will do is that I'll just assign a value to it. So let's say the value of the decay rate constant is, I would say 0.5, just to make things interesting. So I'm going to say the value of the reaction rate coefficient K sub A is going to be 0.5. Okay, so that's one thing I'm going to do. By the way, if I click on the reaction parameters again, the item will disappear, and then if I expand it again, I'm going to get the K sub A. Next, so we have a reaction parameter. We still don't have a reaction process. So what I'm going to now do is that I'll add a reaction. So basically, this is a chemical reaction. So this is the item for chemical reaction. So if I move my mouse to it, you'll see that it says chemical reaction. So So I'm going to just click on that and I'll add a chemical reaction, right? First thing I'm going to do, so it has a name. I'm going to change the name to a decay. So that's the name of the process. It doesn't matter what name you assign to it. Uh, it's never used, but it's just something that is for our information. So here we have a reaction, and the name of the reaction is a underscore decay. So now what I'm going to do is that I'll introduce, I have to introduce these two things. One is the rate expression, and then we have a stoichiometric constant. The rate expression tells us how fast the reaction happens. So essentially it's going to be this rate right here, R sub A is equal to K sub A times A. The stoichiometric constant tells us how much of our chemical constituent A will be consumed or produced as the reaction progresses, right? So in this case, it's going to be -1 because our constituent A will be consumed as a result of a decay, and then we define the reaction rate based on how much A is being consumed. Now, keep in mind that that's not always the case. So sometimes you need to provide stoichiometric constants that are not one. Now, anyways, so the rate expression, all I'm going to do is that I'm going to say it's going to be K sub A times A, and that will give us the rate. So that's the first order decay. It'll just OpenHydroQual will format the expression to a way that it understands. So if you see that the value that you see is different than what you typed in, don't be worried about that. And then the stoichiometric constant for A, as we said, is -1. So we have a -1, and then we have this, and I'm going to save it. So now we have everything set for our first example. We have the first order decay set. What I can do is that I can run it, and then I'll see whether I have to increase the period of the simulation. It's by default it's 1 day, but we can change that. So basically what I'm going to do is that I'll just run, and let's see what we got. So this is all tasks finished. So the simulation is over, and then I'm going to go here and look at, let's say, concentration of A. So I just right click on the reactor icon, go to results, go to A concentration, and you'll see that the concentration of A is declining sort of exponentially. Now if I want to see what happens, let's say maybe 1 day is not enough to see the full picture. So what I'm going to do is that I'll just increase the simulation period. So I go to settings, general settings, and as you can see, by default the simulation start time is 0, the simulation end time is 1. Now what I'm going to do is that I'll change the simulation end time to something other than 1. Now by default, if I click on this value, it's going to give me a date box, so I need to enter a date value, which is not what I want right now. So what I do is I basically right click on the value instead of clicking, and it says a menu pops up that says insert in numerical format. I'm going to click on that one, and then I'll change this to, let's say, 5 days. So that might make it a little more interesting. So I'm going to click on that one. I'll save, and let's run the model again. So I'm going to go here, run, and let's see now what we get. So I just right click on the reactor, and then you can look at the concentration, and you can see kind of the full picture. So we have exponential decay in throughout our simulation period, which is 5 days. Now, okay, so that's the first step. The second step, I'm going to add a new constituent called B, and then this time I'll apply a second order decay to it. So I'll just repeat the process. So let's just add, first of all, let's add our constituent B. So I go here, chemical constituent, I click on this icon, it'll give me a constituent _1. I'm going to change the name to B, right? And then what I will do is that I will add a new reaction parameter K sub B. I'm going to keep the value actually the same as, let's say, K sub A, but it's going to be a different parameter. So what I will do is, let's just add a new reaction parameter, and then I'm going to change the name to K sub B, and in the value I'm going to still assign a 0.5. Okay, so we have the reaction parameter. We have two reaction parameters, K sub A and K sub B. Now I have to add the reaction. By the way, I forgot one step. I need to assign some initial value, initial concentration to constituent B in my reactor. So if you click on the reactor, and if you look at the properties, you'll see this new property added called B concentration. So what I'm going to do is that I'll make that the same as A concentration. So I'm going to start from 2 grams per cubic meters. So we have 2 grams per cubic meters of A and 2 grams per cubic meters of B. Now, next, I haven't added my reaction for the second order reaction for constituent B yet. So let's do that. So what I'm going to do is that I'll go here. I add a new chemical reaction. So then if I go to reactions, I'm going to have a second reaction. It says reaction 1. I'm going to change the name to B decay. And if you see, now we have two stoichiometric coefficients, A stoichiometric constant and B stoichiometric constant. That's if this process of decay of B is actually maybe producing or using some A2. I'm not going to use this at this time, even though I could. So basically, for the reaction rate expression, I'm going to say K sub B times B squared. So this is the rate expression that we got. So that's a second order reaction. And then I'm going to use a stoichiometric constant of -1 for constituent B. Okay. So that's it. I think it should be all set. So I have two reactions going on. One is controls the decay of B, one controls the decay of A, and I think we should be all set. Let me save, and then I'm going to run the model. So run, all tasks finished. Now let's look at, let's say, concentration of B. So this is going to be the concentration of constituent B. I can, also show concentration of A throughout the simulation. And then if I want to compare, I can just copy A and then paste it on B, and this is what you can see. So basically, as you can see, because B is undergoing a second order reaction, it drops faster at the beginning and then it slows down. The drop in the concentration of A should be exponential, and you compare them. Okay, so with that, we are done with the second step. So now what I want to do is that I want to change the reaction controlling A to make it monode kinetics, right? So let's do that. So all I will do is, basically, I'm going to need one more parameter called K sub S, which is going to be our half saturation constant. So let's just add that one. So basically, again, I'm going to click on reaction parameters. I'm going to add a new, so this is my reaction parameter that was added. By default, it's called reaction parameter _1, but I'm going to change it to K sub S. And then the value, since my concentrations vary between like 2 and 0, I'm going to make this value, let's say, 0.6. Okay, so the value of half saturation constant is going to be 0.6. The unit is going to be the same unit as I measure K sub A, concentration of A and B, which is, let's say, milligrams per liter or grams per cubic meters. So So here is what we have. So we have the parameter, and then all I need to do is to go to my reactions here, and I'm going to pick A, decay of A, right? Because that's the one that I want to change. And I'll edit the rate expression. So I'm going to click on this one. I don't need the parentheses, even though OpenHydroQual is going to add them. So what I do is that I will divide this by k sub s. Okay, so it's going to be k sub s plus a. If you look, this is the same form as our, so if you look at this equation, it's the same form as what we have here, right? So the stoichiometric constant for A is going to be still -1. I don't need to change anything else. That's all. All I did was I changed the rate expression from just a simple first order decay to a monode kinetics. So let's see now what happens. So now I can run the model. So here it is. Simulation is finished. Now let's look at, let's say, concentration of A. So here's what we have. It's pretty much linear because we are not getting close to our half saturation constant of 0.5. Now if I want to see more interesting results, probably I can just increase the, I can either increase the simulation time to maybe 10 days, or I can actually make the reaction to go faster. So maybe that's a good idea. So what I'm going to do is I'll just go and change my rate. So under reaction parameters, I have this k sub A, which is the reaction rate. I can make my reaction to go faster by increasing the value of k sub A. So what I'm going to do is that I'll increase the value to, let's say, instead of 0.5, it's now going to be 2, right? So now let's run the model again, and let's look at the results now. So let's say concentration of A. So here's what happens. We have kind of a linear decrease at the beginning until we get to the half saturation constant. The concentration gets close to, or gets to the half saturation constant value of 0.5, and then our reaction turned to an exponential decay. Okay, so that's it. That's how to do the monode. Then the next thing, which is going to take a little bit of time, is now what I want to do is that I want to make the reaction temperature dependent. Now, in order to do that, what I need is that I need to introduce the temperature as a time series. Okay, so I'm going to make up this time series representing the temperature variation during our 5 days of simulation, and then I'm going to use that as the temperature of the reactor, and then I'm going to tweak some parameters to make the reaction temperature dependent. So since I'm using Linux for creating this demonstration, I have to use LibreOffice to create my time series data representing the temperature, but you can use Excel. It's going to work out pretty much the same. So by the way, what I'm going to do is that I'll create this step function. I'll assume that temperature is, let's say, 12 degrees Celsius at the beginning of the simulation. It'll stay at 12 degrees Celsius for half a day, and it'll jump up suddenly to 30 degrees. It'll stay at 30 degrees for 1 day, and then it'll go back to 12 degrees Celsius. So I'm going to show you how to create a time series for that purpose. So all I need to do is to introduce some points representing temperature at different times, right? So I'm going to, at time 0, my temperature, as I said, is going to be 12 degrees Celsius. At time half a day later, actually what I'm going to do is that, let's say at 0.49, right? And I'll show you why I'm doing this. It's still going to be 12. And then at 0.5, it's going to jump up to 30. For 1 day, it's going to remain at 30. So at time 1.5, it's going to still be 30. Then it's going to, at 1.51, it's going to go back to 12. And then it'll remain at 12 degrees Celsius until day 5. Okay, so that's what I have. Now what I have to do is basically all I need to do is to basically make this comma delimited. So you can actually save this as a CSV, and that's going to be your temperature time series. Oh, by the way, let me show you how it looks like. So what I'm going to do is that let's plot this. So I'm going to insert a chart. It's going to be an XY scatter, and I'm going to use this line, and that's all I have. So this is how it works. So basically the y-axis are temperature, x-axis are time axis. So for half a day it's going to be 12, and then it's going to go up to 30. It's going to remain at 30 for one day, and then it's going to fall back to 12, and then the rest of the time the temperature is going to be at 12 degrees Celsius. So what I'm gonna do is that I will just use you can use any text editor. You can use Notepad or TextPad or Notepad++, any ASCII text editor. On Linux, it is going to be gedit. So I'm just gonna copy paste what I created. So I'm gonna copy from here, go to gedit, paste it, and then what you have to do is that basically the delimiter should be a comma, not a tab. So I can just manually change all the tabs, basically replace them with a comma, or I can automate that using this find and replace. So a tab, just replace it with a comma, replace all, and then I need to save this file in some location that I can easily find. So what I'll do is that I'll do it in my Dropbox in this folder called Aquifolium, and then I say temperature, let's call it temperature for reaction example.txt. So I just saved it. So now let's go back to OpenHydroQual and see how to use that. So basically what I have to do is that I have to apply it to my reaction parameter K sub A, because that's what I was planning to do. So I want to make K sub A temperature dependent. So you can do this, similarly apply it to any other reaction parameter as you want to. So now what I want to do is that we have this temperature time series case, and I need to pick the temperature time series data that I just saved, which I called temperature for reaction example right here. So this is the file that I just created. I'm going to pick this one. You can, by the way, look at how it looks like. So if I right click on the value and then plot, you're going to see the same graph, right? So then I need to do two more things too. I have to basically provide a reference temperature, which in this case is going to be 20 degrees Celsius. So we decided that the reference temperature to be 20 degrees Celsius. 20 degrees Celsius is the value that's typically used in water quality modeling. And then the Arrhenius temperature correction factor, that's our theta, and we decided to set that to be 1.05, right? So basically I'm going to make this Arrhenius temperature correction factor to be 1.05, and everything should be set. Now our reaction parameter K sub A is going to be temperature dependent. Now I'll do one more thing. I wanted to just see the results more make the results more interesting. I'm going to reduce the value of K sub A, the base value of K sub A. This is now going to be the value of K sub A at 20 degrees Celsius. I'm going to make this 1, right, to slow down the reaction so that I can see the effects of temperature. So and that's all you have to do to make the reaction temperature dependent. And I'm going to run the model again, and now let's look at the results. I'm going to look at the concentration of A, and here's what we have. So basically it kind of drops more slowly the first half day. Uh, then it'll drop faster because temperature went up, and then we went back to 12 degree. So basically the reaction slows down, and that's all they have. Um, Now, keep in mind what we can do is that we can actually this was all the reactions that we simulated in this case were single component reactions. We can basically easily make them multi-component reactions by defining our reactions that way. So, for example, um, I can just change the rate expression for the decay of B. Let's say it's basically B is reacting with A. So all I can do is that I can just go and change this to times A. So now what we have is that the reaction that is affecting constituent B is going to be K times B times A. So it depends on both B and A. And I can add a, let's say, a stoichiometric constant for A. So A is actually being consumed at the same rate as B, and that's it, and run it and see some results. Now let's just run it. Let's see how our B concentration of B is now changing. So if we look at the concentration of B, it's gonna fall, but it's not gonna reach 1. Now let's see what the reason for that is. So let's look at concentration of A as well. So if I look at A, as you can see, the concentration of A falls to a very small number after, let's say, 2 days or 3 days, and that's why our reaction stops around that time pretty much. So if I paste this, you'll see that as concentration of A goes down, the reaction affecting B slows down. Thank you very much for watching, and look for my future videos.